Okay, yeah.
Yeah, I was just wondering.
Just a second, Rayan. And at 11, just at 10:30. Yeah, Rayan, go ahead.
Yeah, right. I was just wondering if you would be willing to go over the equation again.
Oh, sorry, I can't really hear you. Just give me a second. Okay, go ahead. Go again. Oh, see, there's feedback. Okay, it's going now. Okay, now. I shouldn't have pressed too many buttons. Can you say the question, Rayan, and then Kevin will tell me what you're saying? Because it's hard for me to hear. Sorry about that.
Sure.
Right. I was wondering if you would just be willing to go over the equation again during the recording so we could have it on record.
Okay, he asked.
Yeah, I could do that. Just give me a second. I heard that. Sorry, there's feedback. Just a second, I'm sorry. I just want to get back on.
Yeah, you're straight.
Sorry, just a quick second. I knew we were going to have some technical difficulties the first time. I was actually impressed at how few technical difficulties we had. Okay. Okay, no feedback. Okay, good. Oh, and we have Miss Delise, who was my high school physics teacher, by the way, just put a message. Question should be put in the chat so you have a record. Yeah, good point, Miss Delise. So if you guys could do that too. Okay, so it's recording, so I'll just go over these equations again. So again, I'm just sort of mathematically describing what we talked about conceptually with Stern-Gerlach and sort of the whole intuitive breakthrough we're feeling right now. So I want to calculate the force of my magnetic field in all three directions. So this gradient operator tells me both the component of the magnetic field in three directions and the magnetic moment in those three directions of my atom, or of my electron more precisely. And so that's what this spells out. And of course, a dot product, I think most of you should know what that is, but if you don't, I can explain it. A dot product is simply multiplying each component of the magnetic field with the operator. So I can spell that out. So what is mu dot dr? Right, mu dot, and with the gradient, it's just d dx bx mu x plus d dy by mu y dot. Okay, and any number of degrees of freedom you want to work with. So I have to remind myself that sometimes some of you have not really taken intro physics yet. So if I skip over anything, just let me know. Okay, so this is sort of our mathematical description of Stern-Gerlach. And we're going to focus on the z direction. Okay, so now let's build up the measurement algebra. Let's find a way to sort of describe quantum mechanical measurement. So here's the sort of system I'm going to set up. And I'm going to do this very systematically, step by step. I'm going to say I want to measure some physical quantity A. Okay, maybe momentum, maybe position, maybe velocity. And when I measure that physical quantity A, I get back some measurement of that, A prime. So this is an operation that measures A, right? And I get back some A prime. Okay, and how will we symbolize that? We'll symbolize that with this symbol, a bracket with two A primes. Why do I have two A primes? It might not be so intuitive now, but I'll explain what this symbolism means. It means I'm trying to measure A. That's implicit in my description. I put in an A prime atom and I get an A prime atom out. That's what this means. So I've done two measurements here where I put in an A prime and I get an A prime out. Okay, so that is sort of what we're going to build all our measurement algebra off of, this sort of simple principle, this sort of simple symbolism that comes from our experiment, namely Stern-Gerlach. Okay, so let's write down some of the axioms of this measurement system, so to speak. So clearly, if I have A prime multiplied by another A prime, I should just get back A prime. That identity should hold, and the following identity should also hold. If I have A prime multiplied by A double prime, I get 0. Why is that? So I put in an A prime, I get out an A prime, but I've gotten out an A prime, so I can't put in an A double prime. In other words, when you multiply two of these symbolism measurements, it represents successive measurements of the same property, right? So if I have a successive measurement and I just got out an A prime, where did the A double prime come from, right? In other words, this part of the measurement symbol starts the chain, right? I can start with, I have to start with something that comes from my physical measurement, which I wish to observe. But once I start the chain, I need the same thing here. Because what could even happen here such that I got out an A prime and I magically got an A double prime? So of course, these two identities must hold. And it follows from these two identities actually, I'll write it this way for you guys. The following also follows. If I multiply my measurement algebra by 1, I just get back my original measurement. If I multiply by 0, I get a 0. So these are just some basic operations, very trivial, but it's important to sort of lay down the law and get the full picture of these measurement symbols. Okay, let's continue to build on. You might have been questioning something very important in your intuition when we first learned about this experiment. And I'll elaborate on that in a second. Let's consider the following. Let's consider the measurement where neither A prime or A double prime is selected. In other words, the unselected measurement. How would I represent that in my measurement algebra? So A prime does not equal A double prime. And if I want a non-selected measurement, it would look like this. It would be the additive sum of the two. Also, if I did it for 3. Again, it would be the additive sum. Now, this should be very, very mysterious to you, because in classical physics, there's no such thing as a non-selective measurement. It doesn't really make sense. In quantum mechanics, you should ask yourself the following and contemplate it. I told you that these atoms were going half polarized up, half polarized down. But then the natural question becomes, well, where were they before the measurement? Where was my atom before the measurement? And to that, we have no answer. The best we can do is talk in the scope of probabilities, which is another aspect of quantum mechanics that we're going to have to describe. Before we take the measurement, we have no idea where the particle is. We have no idea. We can say with some certainty it's going to be polarized up and polarized down. And so this is where this word superposition comes in. That before the measurement, the particle is in some superposition of states, which we'll describe as state and state vectors. So this would describe that symbolically. They're additive sums, and it's unclear what I'm getting out, right? It's very unclear. I have no idea. So now let's write this generally. We'll go from some A1, A1, some AN, AN. And this yields the following. This just yields a sum over all my measurements. Okay. Now, this superposition is a very strange thing. And again, you could spend a whole class, a semester, talking about the deep hidden truths underneath superposition. As a physics student, to me, it's just what nature is doing. The fact that it goes against my intuition is none of my business. Nature doesn't care about my intuition. And so keep that in mind as we see more craziness unfold. But what I will say is this. We've introduced a whole new system of mathematics that we're going to need to employ to look at quantum mechanical systems, namely probabilities. But that being said, I want you to remember, when people talk about superposition in the media, they tend to leave out the actual measurement. When the measurement happens, it's definite. There's no probabilities. I know what I got out, an A double prime or an A prime. There's no weirdness at all. There's no quantum mechanical jitterness at all. I know what I get out once I make the measurement. Okay, it's only before that things are confusing. Okay, so building off that probability principle, we have that the sum of all of my measurements must add up to 1, right? That's probability. And of course, I shouldn't say of course, I'm introducing to you your first quantum mechanical device. This is called the completeness relation. And it's important because you need to make sure that all your probabilities add up to 1. We can call it theorem, we'll call it relation. And that's the completeness relation of all vectors. So this is an important first principle. It's straightforward, it's very, very simple, but it's important to think about physics from this point of view now that we've discovered some new portion of reality. Okay, so let's continue to build up. Let's continue to build on. I want you to note the following coincidence. Let's say I'm adding 2 of these. Multiplying 2. Now, let's say I do them the opposite way. And remember, I get something back because these two things are equal. And they're sort of in the middle of the process. I put in an A prime, get out an A double prime. That A double prime has to stay. I get back out an A prime. And so I condense that, which I can do. That's just the physics of what's going on. But if I switch the order, I get back something different. So we also note that our measurement symbols are not commutative. So now I'm going to introduce 2 operators, 2 operations, not operators, operations in quantum mechanics that are very important, that we'll be using all the time. And they don't stem directly from this, but I figured since we've noted whether our measurement symbols are commutative or not, it would be a good idea to introduce these operations. So the first one is the commutator. Right, and then the second one is the anti-commutator. And it will turn out that in quantum mechanics, when this symbol vanishes, when my commuter vanishes, we say that the 2 quantities in the brackets commute, right? When you get a 0 here, when they vanish. It turns out in quantum mechanics, 2 properties that are mutually observable will commute. And so we're going to promote all our dynamical variables, or degrees of freedom, to commutators and describe their commutation relations. So this is super important. Commutation relations, understanding why they work, how they work. I would do some, extra reading on commutators. They're extremely important. And anti-commutators as well. In fact, Dirac, in describing the electron, employed anti-commutators. And you'll see why commutators did not work when we get to field theory. Okay, very good. So let's continue to build up the machinery. Let's look at the following. Okay, so now I have 4 different symbols, and I can write the following relation. This object equals 1 when A2 equals A3, as we've sort of outlined. And it equals 0 when A2 does not equal A3. Okay. So I'm going to write this in a different mathematical form to make it more convenient for us. So we'll use this delta, A2, A3, A1, AIB. What does this mean? This delta A2, A3 is called a Kronecker delta, named after the mathematician Leopold Kronecker. And whenever you see this and you see the symbols inside it, it just means this. It means it's 1 if A2 equals A3, 0 if A2 does not equal A3, and we know that we always get back this measurement symbol. One thing to note, you're going to be seeing these everywhere, okay? And you should kind of start to intuitively put this together. We're dealing with a lot of ones and zeros, right? Somehow our measurements are kind of falling within this range of numbers. And so all our mathematical structure is going to be sort of positioned around a set domain of values that we can obtain, because we're dealing with probabilities. It's also more convenient to work with zeros and ones, makes solving the equations very, very simple. And in fact, we can even employ a certain set of vectors in physics to only deal with ones and zeros, which I'll describe in a second. And again, if you have questions, feel free to type them in. And Coven, just read the chat, actually. That's better, because of the feedback. Yeah. Okay, very good. Okay, now I want you to note the following physical process. And this physical process is going to take you into the conventional quantum mechanical notation that you've probably seen all the time. So let's look at this. Okay, what's going on here physically? Somehow I put in an A prime and I get out an A double prime. Somehow the in state is an A prime, the out state is an A double prime. The A prime particle is destroyed. The A double prime particle is created. So in Dirac's notation, this is Dirac's Brockett notation, which is what we'll use for the entirety of the class. We symbolize this with the following. And what this represents is just what I described, the destruction of A prime and the creation of A double prime. The out state, the in state, the in state, the out state. And so now we're sort of learning the formalism a little bit more. This is the notation you'll see in any physics paper talking about quantum mechanics. And Dirac invented it, and it turns out this is a really nice notation to work with. The more exercises you do with it, the more comfortable you'll feel with it. It's very important to make this kind of a second language. So let's work out the last example we just talked about. Let's look more in depth into it. Now, using the last definition, I can rewrite this as the following. There's a bracket there. I ran out of room. Actually, let me rewrite that just because it's your first time looking at something like this. So I want to make sure it's clear. So now we've written out that expression in Brockett notation. And just for convention, we get rid of these double lines. From now on. Okay, great. So let's think about this for a little bit, okay? We know what this object represents. What does this object represent? What have we just constructed here? This turns out to be a very important combination. So this object equals delta A2, A3, and it equals a number. So we call this combination of vectors, I said vectors, I shouldn't have said vectors yet. We're going to define these objects as vectors. But you see where I'm going now. This object is called a scalar product. Why? Because when I multiply, I get a scalar. Sorry, this combination yields a scalar. Now you can see where I'm going with this now. I gave it away just because I'm so used to describing these objects as vectors. You're going to notice that the objects inside here are vectors, okay? And we call this particular object, for example, or this particular object, a state. So these are states. They're states of whatever physical property we're trying to describe. Moreover, we call them state vectors. Okay, and each vector in our space, we're not going to talk about vector spaces in this class. That's a little advanced, or Hilbert spaces if you want to look into this more in depth. But each vector in our space forms the complete set of vectors corresponding to that physical property. And there's a special class of vectors in physics that are all normalized to 1 and that are orthogonal with each other, orthogonal unit vectors. So you might recall a unit vector is equal to EK, E sub k, where k runs from 1, 2, and 3. We have the following relations: EK dotted with some other basis vector EL equals the Kronecker delta. And I'll just write this out like this. I'm going to explain this a little bit more in depth. So what are EK? And by the way, I'm writing this up here because our state vectors have the same properties as these vectors from classical physics. So what is E sub k? Those of you that have taken presumably physics C must have been introduced to these. E sub k are a set of unit vectors. They could be in any basis. What do I mean by basis? Basis just means what coordinate system I'm working in. You'll see that we're not always going to be working in Cartesian coordinates. Most often we're going to be working in spherical coordinates because it's more convenient choice to describe the physics. And it runs from 1 to 3 because our unit vector is in 3 directions. We're working with 3 spatial dimensions. If I take the dot product, they're perpendicular unit vectors, right? Unit vectors are always perpendicular to one another, right? Therefore, they're orthogonal, okay? They are all equal to 1, normalized to 1. They could equal like cosine theta r, but that would be for a black hole. But in our cases, they're all 1. And let's think about this. If I take the dot product, what am I doing? I'm just multiplying each individual component. So let's say EK is the x direction, and EL is also the x direction. So EK times EL gives you back a 1, right? So Kronecker delta, K equals L, you get back a 1. Now let's say they're in opposite directions. I get a 0, right? Because they're orthogonal to one another. And this complete set of vectors that are normalized to 1 and mutually perpendicular or orthogonal, we call it orthonormal. So in quantum mechanics, it's very important to remember we will always be working in an orthonormal basis. Orthonormal basis, because it makes our calculations easier. We can define our state vectors as a set of orthonormal vectors. If you want to look more in depth to this, it's a state of orthonormal vectors in a Hilbert space, which is a complex vector space. And the reason it's a complex vector space, we're going to get to more weirdness, but the Hilbert space has a lot of properties. Sorry.
There's a question
Sure.
from Ryan again. He said, how do you treat the before/after states, the vector states, as directions?
Yes, exactly. Very good question. So you will see how these vectors manifest themselves geometrically. And they're going to manifest themselves geometrically in a complex plane because we're going to see in a second that our state vectors must be complex. But good question. And to that question, I'll say one quick thing. See, classical mechanics, the reason it's so intuitive is because you can visualize it. In quantum mechanics, since we're probing such small length scales, the mathematics becomes crucial, right? Because the mathematics is our only sort of line to get to all the fuzziness. So I just say this to some, you guys are first learning the subject. It's okay if things aren't completely clear intuitively yet. In fact, one of my heroes, Richard Feynman, said, no one understands quantum mechanics, not even me. And he won a Nobel Prize for his path integral on quantum electrodynamics. Both two things that we'll be learning, path integral at the end of this term, QED next term. But someone that brilliant said that statement. So just something to keep in mind. It takes time and it takes some massaging to get used to what's going on, but very good observation. And it's good to think geometrically about things as well. And we'll do a lot of geometry shortly. Okay, excellent. Okay, so we've introduced brackets. We have sort of started to develop some of the machinery. Now I want to look at a particular example. So my magnets were right down the middle when I fired my beam. And what we can say, if we draw a coordinate system, right, we can say that our magnets were at 90 degrees perpendicular to some other vector pointing in 180 up, 180 down. Okay, so let's say our magnet's at 90 degrees. Now we wish to write a set of probabilities to describe the magnetic moments in the 90-degree angle. So the geometry here is could be a little confusing, probably won't be. It's pretty straightforward. If you have a geometrical question, feel free to ask me tomorrow morning, and I'll go over the picture more in depth of what it actually looks like. But I'm just going to work through it quickly for now. And I'm just going to derive for you 4 probabilities. And I'm going to do it fast because it's just some algebra and geometry. It's not very complicated. But what am I going to derive for you? I'm going to derive for you a P, so a probability of plus plus. What does that mean? That's the probability of getting an electron in the plus direction twice in a row, plus plus. P of minus plus, P of plus minus, and P of minus minus, right? So both down, one up, one down, one down, one up. And I'm going to derive 4 probabilities for you for any general theta. Okay, for any general theta, any angle you could move the magnets at. So I'm going to do this kind of fast. Just fair warning, this is the first class, so I'm going slower than usual. Usually I'm a lot faster, but I just want you guys to really think about the ideas today. The mathematics is something you'll have to worry about on the problems. So, okay, so let's just do it. So I'm just going to use cosine theta as my sort of reference angle for how I turn the magnets. So I can get the following relation. If I'm considering an initial I'm considering the initial particle being polarized up. Then I get 2 probabilities. And just doing some algebra, and working out the geometry, I derive my first 2. Let me just think this through. Yep, I derive my first 2 probabilities. P of plus minus. And to get these final 2 values, I just use some basic trig identities, which I'm going to write down now. I like to say this to new pupils of the subject. You can never know enough identities. Basically, all of the computation that happens is just remembering the right identity. And that's a good tip as you go along this physics journey. Okay, so let's just get these 2 identities and get the full spectrum of angles from 0 to pi. Okay, so I have this. All right, and I can just write this out in this fashion as well. Which yields the following. When you see 3 dots, that just means therefore. And I use it often, so just for a convention. Okay, and so now I get the full spectrum of angles, right? So if I have sine squared of an angle theta, I have to take the difference between theta and pi and take the cosine, and I get an equivalence using the identity and just some geometry. And so now I can write down the 4 probabilities that I described. Also, if I'm going going too fast, if you're having trouble writing things, let me know. I can stop, you can look at the board. Another quick thing to note, even though I'm recording these, the reason I'd like you guys to come to class, and I request that you only ask for the lecture recording if you weren't able to come, okay? Just so we don't have like 2 people here next Saturday morning. Is that fair? And just to, you know, keep it, be somewhat of a routine.
I have a question for Esha. Can you rewrite the last?
Yeah, I can rewrite. The last lines, I mean, that's the identity. The rest is just kind of just some manipulations. So you get this identity. Okay. So, you know, you're going to be working with a lot of trig. Should brush up on it.
Time check. You have 13 minutes till 10:30.
Okay, very good. We're on good time. Okay, excellent. So let's tread through. And first I'll write down the 4 probabilities for you. For any general theta. Yes, good. So this gives us the full probabilities for any general sort of angle. And in the homework, you're going to be asked to do this sort of exercise for an angle at for a particular value of theta in a particular direction. And you're going to write down all the probabilities and work up the geometry and that kind of thing. And you'll find out something extremely strange when you look in the particular direction I asked you, which will be interesting. Okay, very good. So now I'm going to introduce to you another fundamental quantum mechanical concept, namely the concept of the operator. Okay, I sort of wrote a capital A at the beginning of class, a capital A, and I was like, this is the physical quantity I want to get, right? I want to get momentum. So what do you do when you want momentum in classical mechanics? You use P equals mv, you have the m, you have the v, you solve. Okay, great, wonderful. And I get my dynamical variable. Turns out, doesn't work like that in quantum mechanics. And we're not going to talk about momentum in particular today. We're going to talk about this generally and build it up generally. I'm just sort of spelling it out for you to sort of spell out where we're going. In quantum mechanics, all of our dynamical variables get promoted to something called an operator. An operator is it's an operation. It's an operation on our state vector that yields back a particular observable. So you can see where I'm going with this. The momentum operator acts on a state vector and yields back a number, which is the momentum, right? Yields back a scalar. So let's just talk about a general operator. Let's describe this general operator in some general ways, okay? And let's see how it behaves, okay? And I encourage you to play around with your own operators, make up some fancy things and see what happens. And hopefully this bracket notation is becoming like English. You can sort of look at a whole system, see what's the in state, the out state, see what operators are acting and so on. Could you repeat what you said about the momentum operator from Richa? Is that how you pronounce it?
It's Richa.
Richa, okay. Yeah, Richa. So the momentum operator is an operation, right? So it could be like, it could multiply the state vector, it might add the state vector. In the case of quantum mechanics, which we'll find out, it will take the partial derivative, time derivative of h bar over I of the operator, but we'll get there. But basically the operator acts on the state vector and yields back an observable quantity, yields back a value for momentum, like when you do the P equals MV, yields back something. And after the measurement, so it is a definite momentum state, a definite momentum value. Does that make sense?
Yeah.
Okay, good. Excellent. So let's call a general operator, we'll call it M of B. And let's look at three cases. Okay, I'm gonna construct 3 operators for you. And in the homework, you get guided through 3 more constructions. Okay, so let's do it. Let's look at the first case. I wish to construct, and we'll define this, and we'll say that this M of B yields back a B prime, okay? Right, remember we said the capital A yields an A prime? We'll say for notation's sake, this M of B yields back a B prime, except now, instead of just writing a capital B, I'm sort of defining the operation to get back the physical state a bit more specifically. Okay, so I wish to construct an operator such that I only get back B prime. Okay, how would I do that? Let's work it out. So I work it out by constructing something like this. Okay, so now let's say I want to know the probability of putting in an A prime atom with the operator acting on my A prime state. How would I describe that? So I'd have P of A prime M of B equals this. And we should notice something. So this is the operator that only yields B prime. Therefore, this equals delta A prime B prime times delta B prime A prime. Therefore, you can only get something out if B prime equals A prime. Okay. So I've constructed an operator. I've acted it on one state, and this notation yields this combination, right? You get a bracket of A prime, right? And the operator gets sandwiched in between, always, okay? So there we go. That's my first situation. Let's do the second one. Now I wish to construct an operator M of B such that I get back the original particle I put in. Okay, how would I do that? Well, I'll use the completeness relation of states. So M of B equals now the sum over B prime, this quantity, right? And this is called the and this equals 1, obviously. And this is defined as, should put it defined as, the identity operator. So this is your first real quantum mechanical operator. Okay, and let's do the same game. I should make this a bit more explicit that I'm taking the sum over B prime. Okay. And as you can see, doing the manipulations, I just get back A prime. I get back what I put in. Yeah.
5 minutes.
5 minutes? Okay, good. The reason I say that, guys, at 10:30, we're going till 11, but from 10:30 to 10:35, we'll take a 5-minute break. Is anyone opposed to that? Okay, cool. The one thing I'll say is we might not always get a break. It's just today's a little light. So that's when we'll take a little breather. But sometimes we might be going past 11 when things get a little tight. So, but anyways, okay. So you do this by the way, Kevin, I can see the time now.
Oh,
It's showing, yeah, so no need to. Okay, so you get back your A prime. Very good. Now let's construct one more operator. Let's construct a non-selective operator. Let's construct an operator such that I don't get either B prime or some B double prime. And these seem trivial, they kind of are. I'm just doing them for you to get a feel for how these work and the kinds of constructions you can make. Let's play the same game. This is really just okay, and now I get the non-selective measurement where I don't get either. I'm not sure. And I really shouldn't even be calling this a non-selective measurement, right? I mean, it's just a non-selective set of states. And we're really not going to be working with an object like this. I mean, it's just not going to come up. Unless, of course, my additive bras and kets are not related, right? So if this had C primes and D primes, and this had A primes and B primes, they both yield scalars, right? Okay. Very good. Any questions? Okay. Nice. Okay. So let's take a little 5-minute break till 10:30. Just 10:32. I'll give you the full 5 minutes, and we'll come right back and continue. Okay? Great. Yeah, these are like Zoom. It's like Zoom stretch time now. I'm so used to a stretch break now that I have to put it in. I really don't, for those of you who've taken classes with me before, usually we're in person and it's so engaging. So that's why I have all of you in gallery. So when I ask a question, do shake your head. I can see your heads. I like to engage with people. So this is very, very strange for me. But we'll get used to it together. And hopefully when Corona dies, we'll all meet up in person on campus or something cool. So I'll be right back. Oh my God. Brianna has a Kermit going wild. Let's see, where are some of you people from? Who can I see? Okay, Vu Giang, where are you from?
I'm from Virginia Beach.
Virginia Beach, welcome. Lizzie?
I'm from Woodbridge, New Jersey.
New Jersey, you're my neighbor. I'm in New York. Sneh?
Hello? Yeah, I'm from India.
You're from India, wow. So this is very odd timing for you, my apologies.
Oh, it's actually pretty good.
That's some determination right there. Who else is on my screen? Andrew.
I'm from Michigan.
Michigan, nice.
Yep.
Who else? Jenna?
I'm from California.
California, okay. Oh wow, it's early for you too. Oh my gosh, I feel so bad, but I have to be a little selfish with time, unfortunately. Olha?
I'm from Ukraine.
Ukraine. Wow, we have a global class. You see, this is the one benefit of Zoom. All around the world, you guys have come in to learn these beautiful ideas about nature. It's very, very exciting. Very excellent. Who else? Who's this guy? Ajay. Who's Ajay? I'm just kidding. Ajay's like my cousin brother. That's why I had to call him out. He comes to every single thing I do, so he's the consistent visitor. Ivy and Nikki. I think we have a sibling duo.
Yeah, we're from Canada.
Canada. Hello, welcome, welcome. Very nice. You could go for some Tim Hortons. Okay, great. Let's continue. Okay, excellent. So let's define two more relations. Let's look at the following, okay? Let's construct this object and define this operation. So this is my bracket, and we're gonna call this operation, so it's not only a scalar product, it's a probability amplitude, okay? That's, people refer to these things with these terminology, but this terminology, so I wanna make sure you've heard it, just so when you look in the literature or if we write something together, you kind of know the jargon, so. Okay, and now what I can do to take a successive measurement, well, let me backtrack. We know something detrimental will happen if we get back a negative probability, okay? A negative probability is bad. So anytime we square our probability amplitudes, we have to take the norm of that square to ensure positive probabilities. So that's all I'm going to sort of spell out here, that we always take the norm squared. And I'll just write, this is an arbitrary combination. Okay. And we might want to take successive measurements. We might want to, this would be a compounded measurement, right? Because you get the measurement and then you do it again. And I'll just make this really clear. That part of quantum mechanics is not mysterious. If you take a measurement, complete the cycle, you get back a cupcake. If you do that same measurement again on that system, you'll get back a cupcake, guys. You won't get back something weird. So compounded measurements yield the same result. That holds true. So this relationship, if you've been questioning your intuition, you might be questioning this, but don't question it. This is fine, and we just take the norm. You're gonna see me take norms a lot, right? I'm gonna write the norm squared of a lot of things, and I keep the norms because I need positive values. I can't have negatives. Very good. Now, let's talk about another weird thing. So as a theory student, as a theory person, people often like to look at mathematical beauty. Okay. I'll just give you my 2 cents. I think it is absolutely insane, yes, insane, that mathematics actually predicts anything about nature at all. I think the fact that we can scribble some symbols on a piece of paper with our pencils and talk about the curvature of space-time, talk about a hydrogen atom, even describe the Stern-Gerlach experiment is quite extraordinary. And to that effect, there are some deep mathematical mysteries that unveil themselves in our study of physics. Why do they unveil themselves in this way? Again, we don't know. So what is one of those mysteries in this context? It's the necessity of complex numbers. So you're going to see explicitly why we can only use complex numbers, okay? I'll give you the explicit answer. So the F equals ma, so to speak, of quantum mechanics is the Schrodinger equation. And for those of you who've never taken physics, F equals ma is Newton's equation of dynamics. It tells you how the system will evolve, right? So the F equals ma of quantum mechanics is the Schrodinger equation. And the Schrodinger equation tells you how a quantum mechanical system will evolve. Turns out you cannot solve the Schrodinger equation without complex numbers. If you use real numbers, you get complex answers, and we can't observe a complex number. Okay, observables need to be real. And so these eyes start popping up everywhere, which is quite crazy. And one of the consequences to that is this. If I have the following scalar product, it's equal to this set of state vectors backwards, but the complex conjugate of this set of vectors. And it will turn out that when we use matrices, right, when we move to our matrix representation of quantum mechanics, right, we're going to define our state vectors in matrices, right, depending on what we're describing. It turns out that we won't only need the complex conjugate of every observable, we will also need the transpose of the matrix in which the observables lie, which right now, that's a technical point. We'll probably get to that next week. But that combination is called a Hermitian conjugate. So really, in quantum mechanics, all observables have these properties. And it's just a mathematical structure. It's just the way the mathematics worked out. There's no physical significance to the statement that all observables are Hermitian. It's just a mathematical consequence. In fact, we'll see that these objects called wave functions must all be complex. That's another condition. And these wave functions, we haven't just talked about anything with waves or wave particle duality or anything. We'll get to that. These wave functions are all complex. You'll never see a real wave function. And that's the Greek letter psi. And it turns out that in the Schrodinger equation, we have psi's on both sides as state vectors. And we have an operator. We always denote operators with hats, but you know, we're gonna cover this soon. This is the Hamiltonian, and it yields back an energy, it yields back a number. And I'll give you some more terminology. You don't have to write it down, I'll just say it. These are called eigenvalues. And for those of you who read the syllabus, you said that I said, you know, it would be good to review eigenvalues, because eigenvalues will be our observable quantities that we get back when we solve this thing. Okay, so it's all going to fit in very nicely mathematically. Okay, here's another thing we need to think about that might not be initially obvious, but it's something that is quite strange. There's still some fuzziness in the actual operation of taking a measurement. Okay, in some sense, you can consider measurement as something that's disturbing our system. So in that sense, we can't always definitely state how the measurement will take place, right? When I sandwich the operators in between. So we can define this operator, and I'll explain why I use this. So m sub b equals e to the I phi, and we'll just say that this corresponds to b prime again, b prime. In other words, I can always shift. And now here's where you need to think geometrically, right? All of our state vectors lie in the complex plane, right? They're all complex. So they all lie in the complex plane, right? Where on the x-axis you have your real part, y-axis you have your imaginary part, and so on. So I can really shift my operator by any angle phi in the complex plane and get the same result, right? The same physics will apply by any arbitrary phi of me shifting all my state vectors, right? In other words, if I drop a ball here and it lands, and I drop the ball in the other room from the same height, I get the same result. The physics must be the same. The laws of physics don't change under translations, under me translating from this room to the next. This is called a symmetry. This is a symmetry. And you're going to see that particle physics people love symmetries, mathematical symmetries. These symmetries yield a lot of insight. And so we see our first symmetry here. The symmetry, this is called a phase transformation. A phase is the angle by which we're moving our coordinates. Okay, so let's work this out. Let's write some things. So now I can write this state vector, for example, set of state vectors as the following. So I can just move it by any arbitrary phase. Okay, and let's write the complex conjugate version of that. For those of you that are a bit rusty on what complex conjugation means, it's a very simple operation. It just means that all our i's become minus i's. You just change the sign of the imaginary number. So let's do the following. Let's just write what I just wrote over the complex conjugates of my state vectors. This should really be a sum over B. Okay, just changes the sign. Trivial, but good to spell out on a first class. Okay, so we've had our phase operations, and again, these phase operations ought to maintain this, and this is why the norm is so important. Some arbitrary, call it alpha, times some arbitrary alpha is equal to the norm of that arbitrary alpha squared equals 1. And back to, I forget who asked the question. Someone asked about geometries. Now you're starting to see the geometrical picture of all of this and how all our state vectors will lie in the complex plane. Very good. And I'll just write this out explicitly using this identity. Right, and so this gives you the full spectrum of possible, and we'll just call this operator a B prime again, being sloppy with notation, but it is what it is. That should be a cos. No, this should be a cos. My bad. Okay, cosine. It gives you the full spectrum. Okay. So we're going to end on this last object of quantum mechanics, and it's called an expectation value. So the expectation value is defined as this. It's 2 brackets, and let's just say it's respect to A prime. So what does this mean? The expectation value is the average value of that physical quantity I'm looking at. And an average value would come from repeated measurements, right? If you did an experiment, you did it separately, you'd get different probabilities, you'd take the average value. And this obviously means nothing in classical physics. In the quantum world, it means a great deal. So how do I represent this? I'm not going to go too in depth with this. If you have questions, you can work it out. Okay, so let's just write out another probability. This yields my expectation value. Nothing kind of crazy. It's kind of straightforward. I can also take any multiplicative constant of my expectation value without affecting the result. How do I show that mathematically? What if I want to create an object like this? What does that look like? Okay, and let's just write these out again as well. I shouldn't write it like that. I should just write it as it follows. So I can construct something like this. Okay, and I can even go up to any multiplicative constant. Okay, where this is just a multiplicative series. And if you follow the steps, you derive this final relation, which will give you the full range of measurements. And you should play around with the expression I'm about to write. And if you want to go over all the algebra to get there, come tomorrow. But it's kind of a lot. You can write out this series of successive measurements as a power series that takes on the following, has to equal 1. How do I want to do this? Yeah, sum over b prime, multiplicative sum. This relationship just gives you the full scope of compounded measurements. And you can work this out algebraically as a power series in b prime. Also, those of you that can't make it sometimes, I'd like you to be here as often as possible. Someone is typing lecture notes for me. As you know, we're putting together a little textbook with all this material. I don't follow notes when I do lectures, so there might be things in the notes that I didn't cover. Just ask me if you're confused. There might also be things we cover in lecture that aren't in the notes. So just fair warning, because I don't really use notes when I do lecture. Okay, great. So now we've sort of constructed the quantum mechanical mathematical structure, and you should note that it all comes from our intuition from one experiment. And this is quite remarkable that we can analyze a whole set of physical phenomena from one experiment. And this is really how it worked out. And for those of you that want to become physics students, become physicists, and so on, I strongly believe every good physics scholar should read on the history of physics. And the history of quantum mechanics is quite remarkable. And if you come tomorrow in the morning over breakfast, I can tell you about the history of quantum mechanics. It's quite remarkable. These people really, really were shocked when they found this experiment, and then theorists sort of ran to the races to describe this mathematically. Interesting side note, Einstein did not like this indeterminacy of quantum mechanics. Einstein was strongly against it until his deathbed. And when he tried to find a unified theory of all the fundamental forces, he tried to find one without quantum mechanics. Didn't work out so well for him, and didn't work out so well for all of us who are still trying to find a unified theory of all the forces that can be predicted experimentally. Okay, great. So what we're going to do next class, so I will post a problem set right after class because it's typed up. You can turn that in by next Saturday at 5, I think was the day and time. And I made an email for where you could turn those in. I think it's qmpsets@gmail, something like that. Gabe will be doing a problem solving session next Saturday, right after this class. So I won't be here. But for now, I'm going to stick around, and I'm just going to take a little 2-minute break, and then I'll come back. And for those of you that want to talk about the class, tell me about yourselves, talk about what we just, not about what we just, anything. If you want to talk about what we just covered, we can do that. I'd like to get to know you guys better because, like I said, this is a strange kind of world we're living in now where we're all virtual. But hey, we have people from Ukraine, we have people from Canada, we have people from India, we have people from California. We couldn't do that on 116th Street at Columbia. So I think that's pretty cool that we're able to do this virtually, in a sense. Okay, so hopefully you have some intuition, however much intuition you can get from this little procedure. And next class, we'll look at a kind of measurement algebra that is more conducive to spin. So we really haven't talked about spin 1/2 and sort of a mathematical description of spin 1/2. And so that's what we're going to do. And the kind of algebra we're going to build up is the Pauli algebra, for those of you that want to get ahead, from this German physicist named Wolfgang Pauli, who was one of the pioneers of quantum mechanics. Pauli exclusion principle, for those of you that have heard, that no electron. Where will we access the lecture notes? Yeah, so just email me if you want lecture notes. Again, at the end of the course, I'll put them all online, but those are really for people that can't make it, right? I want to give you an incentive to come here. Otherwise it's not very conducive to learning. If you really can't, I'll send them to you, but I really prefer not to send them every week to the same people. Also because I'm going to be falling behind on them. I'm sure the person typing them is not going to be able to keep up with me because LaTeX is quite annoying for those of you that know. But where was I? Right, so the Pauli algebra will describe these spin 1/2 systems, and from the Pauli algebra, we'll begin to create our matrix formulation. Right, we're going to start putting state vectors into matrices and sort of developing the whole program of quantum mechanics. Okay, any last questions? Okay, it was a pleasure seeing all of you here today. I hope you stick with us. I really believe everyone can do this kind of thing. I think when people see squiggly symbols on a blackboard, they get intimidated. I just think that's silly. I like to tell people, if you want to play cello like Yo-Yo Ma, you're not going to play cello like Yo-Yo Ma in a minute. It's going to take you a long time. And it's similar to learning anything. It takes quite a bit of dedication, but I think anyone can master it. So I hope you stick along and sort of don't get dissuaded if things get a little difficult. Okay, great. Good to see you. One more quick thing. Can Bob Danning, Grace Vangi Delise, Esha Singh, Adam, Angelina, and Ajay stay on the line, along with those of you that want to stay in chat, because those are the people who have been with me for a long time and I haven't seen them in a while and I'd like to just catch up with them. But for those of you that want to stay on, feel free. I'll be back on right at 11. Okay? Again, thanks for joining in. Thanks, guys.
All right, good to see all of you. Oh, a lot of you have stuck around. Excellent. Okay, so I guess we can kind of, I'd like to get to know some of you. So we'll just go in order and we can chat if you have anything you want to talk about. But my good old folk, so I see Bob, you're the first one. So Bob, we'll wait for you. We'll chat at the end because I want to catch up with you a bit more. So I'll just go in order, just because we have some time today and I'd like to know who's in the class. If you have any questions or concerns. Okay, who's on my list? Or let me do it this way. If anyone has anything, pop in. I think, Adam, I hear a lot of feedback. So if you don't mind just muting yourself. Okay. Okay, so anyone who has any thoughts, questions, concerns, don't feel afraid. We're very open in our group, as those of you who have taken classes with me before know.
Hey.
I should try and cover the requisites for mathematics. Recommend any resources. Okay, that's Sneh. Is that something other people are thinking about too with mathematics? Okay, good. Okay, so this is where it gets a little tricky. I tried and made the point that quantum mechanics is more of a mathematically driven subject. But what I'll say is that there are some really good resources you could use to learn the subject. The best textbook on linear algebra is by this guy named Gilbert Strang. It's called An Introduction to Linear Algebra. There's literally copies everywhere. Literally every undergraduate uses this book by Gilbert Strang. Probably PDFs. You could find probably a used copy for 10 bucks probably. And it's a wonderful textbook. And what I recommend is just going in there and looking at the sections as we introduce them, right? So next week we'll look at traces, we'll look at eigenvectors, we'll look at eigenvalues, we'll look at matrix operations. And so I think that would be the, also just a quick thing. Now we're just discussing now, we have a smaller group. So you don't have to type in the chat. I'd rather hear your voices and talk to people. If you really can't, then type in the chat. And if you really can't have your cameras on, don't have them on. But I strongly encourage you to turn them on just so I can put some faces to names. This has become the new world where we have to talk over chat, which is not fun. Would a knowledge of AP calculus and basic linear algebra suffice? Look, I think a lot of folks have been asking me about this, kind of the prerequisites. And I tried to make this evident, but I think I'll just spell it out more clearly. I really believe you can pick up everything. It's just a matter of how much time you'd like to put in. It's like anything. If you don't put in enough time, you won't feel comfortable with the material, okay? So would a knowledge of AP calculus and I think basic linear algebra suffice? It might. I don't know. I haven't taken AP calculus in a long time. I don't know. I really don't know. So it's tough for me to answer that question, but I can speak generally that I think you can learn everything. It's not very, I don't know why it's still recording. Sorry, we don't need to record this.